Welcome back to the course entitled Symmetry, Stereochemistry and Applications. In the previous lecture, we were discussing about various organic rearrangement reactions, and in that we have discussed about the Hofmann rearrangement reaction, which is a reaction where you can treat an amide and convert it into a corresponding amine by shortening the chain by one carbon. So, in that context, we would like to now discuss a couple more similar rearrangement reactions. So, the first one that we would like to discuss now is called the Lossen rearrangement reactions. The Lossen rearrangement reaction. This reaction is a thermal, that means it happens with the influence of heat, acid or base catalyzed, it is intramolecular, conversion of hydroxamic acid to the corresponding O-acyl or O-aryl derivatives to corresponding isocyanates. So, here this RCO NHOH, which is called the hydroxamic acid, in acid catalyzed condition under heat forms the isocyanate, and the corresponding hydrolysis of this isocyanate leads to the primary amine, as we have seen in case of Hofmann rearrangement reaction. So, let us look at the mechanism of this reaction. So, let us see the base catalyzed mechanism first. So, this is a deprotonation step. After this deprotonation, this alkyl group migrates from carbon to nitrogen, and N double bond C is formed in step 2. with elimination of OH group as well. So, now this isocyanate, as usual, and just like in the previous reaction, in presence of water releases carbon dioxide and gets converted to the primary amine, as we have seen in the previous day's class. So, if you could remember this mechanism of the carbamic acid reacting with the corresponding water molecule, and it forms the corresponding amine as usual. So, you see here this isocyanate first reacts with water to form the carbamic acid, and that carbamic acid releases carbon dioxide to form the corresponding amine. So, this is the Lossen rearrangement reaction. This is Lossen rearrangement reaction that one can use in various organic synthesis. A similar rearrangement reaction is called courteous rearrangement, where RCOCl, that is acid chloride, is first treated with sodium azide. With the elimination of NaCl, it forms the acid azide, so this is acyl chloride, forms acyl azide, and then the migration of R group takes place from the carbon to the adjacent nitrogen with elimination of nitrogen gas and the corresponding pi bond formation. It forms the isocyanate once again. So, then this isocyanate can easily be hydrolyzed to form the corresponding RNH2, that is the amine, with the elimination of CO2 from the reaction medium. So, this particular carbon is released as carbon dioxide in all these reactions, and we get a shortened amine. So, what we see is that all the three Hofmann, Lossen and courteous rearrangement reactions take place on three different types of substrates: amides, hydroxamic acid and the acyl azide to form a shortened amine. So, these reactions can be used to synthesize various organic amines in the laboratory. Now, let us try to see the reaction mechanism of another very important rearrangement reaction called the Beckmann rearrangement reaction. So, in this case, an oxime is converted to an amide in Beckmann rearrangement reaction. An oxime is formed by treating an aldehyde or a ketone with hydroxyl amine. The OH group of the ketoxime, that is R2C double bond NOH, or aldoxime, that is RCH double bond NOH, can become a leaving group by tosylation. So, the reaction is like this. So, this R group migrates from the transposition of this leaving water molecule, and this nitrilium ion is formed. This nitrilium ion then reacts with water molecule to form this compound, which then further rearranges to form the corresponding amide. So, in this reaction, the product that is formed is an amide from a particular oxime. So, this OH group becomes a leaving group after taking up a proton, and then the nitrilium ion reacts with water that is present in the medium to form this intermediate, which then easily rearranges to form the corresponding amide. So, this amide is formed from the ketoxime. So, what happened is the group which is trans to the oxime is found to move or found to migrate from one carbon to the adjacent nitrogen, and we will see some application of this reaction mechanism. The first example is this one. Suppose you have an oxime which is like this. So, you do a acid catalyzed reaction under heating condition. So, what it does is it forms the protonates the OH group first and forms OH2 plus. Then this group from the transposition moves to nitrogen and water is eliminated. As a result, the ring expansion takes place and a double bond is formed here with a plus sign. So, then the water molecule gets attached here and it forms this intermediate, which then rearranges to form this 7-membered ring, which is called the caprolactum. So, here what we see is a ring expansion reaction taking place through a rearrangement reaction. So, what we understand about this Beckmann rearrangement is a stereospecific reaction, and the group trans to the OH group migrates. So, if we have a compound where pH and methyl groups are present and the oxime is such that the pH is in the trans position with respect to the OH group, then the product would be this one. And if the methyl group is in trans position with respect to the OH group, then this will be the product. So, what is seen in case of a Beckmann rearrangement starting from a ketone? Let us see what happens. If you start doing a reaction from this particular ketone, that is 2-pentanone, first if we treat this with hydroxylamine, what we would get are two different oximes. In a ratio of 75:25, and then when we do Beckmann rearrangement, we would get a product which is this one, when this group migrates there, we have 3 carbon atoms there, and this results into 75% of that product. In addition, when this methyl group migrates, one would get this as a minor product. So, by looking at the ratio of the products, one can identify what was the preference for the formation of hydroxylamine, the formation of the oxime with the reaction of hydroxylamine on the corresponding ketone. So, the ratio of the product tells you the procedure of reaction mechanism. Let us now try to see a different type of rearrangement reaction called the claisen rearrangement reaction. Here aryl ethers undergo claisen rearrangement when heated to about 200 degrees centigrade in an inert high boiling solvent. This reaction the migration of allyl group from ether oxygen atom to the ring carbon at the ortho or at the para position through a concerted reaction mechanism. So, the reaction is this one. In case the ortho position is blocked, suppose for this type of substrate where the ortho position is blocked by methyl groups, then in this reaction the para product is also formed. Right. So, one can see ortho migration if the ortho position is free. If the ortho position is blocked, then one can expect a para migration product to form in this particular reaction. I have indicated that it is a concerted reaction mechanism. The proof of such statement is the following. Suppose if we had taken a mixture of two compounds, one with a phenyl substitution and other without any substitution, and had taken a mixture of these two compounds in a given solvent at about 200 degrees centigrade, the product that would form are these two. So, from this is the product, from this is the product. No cross product is formed, which indicates the reaction takes place through a concerted mechanism, through a cyclic intermediate. So, one can think of writing the reaction intermediate reaction mechanism like this. So, this is the alpha carbon, this is beta, that is gamma. When we heat in a solvent, the bond formation takes place from there to this bond moves here and that forms a double bond. So, what we end up getting is this reaction intermediate, which then further rearranges to give you the final product. So, this is a concerted reaction mechanism, and one can draw the corresponding transition state of this reaction as this. Which essentially means the dotted lines are bonds that are either in the process of formation or in the process of breaking. So, this bond is forming, this bond is breaking, this bond is forming, this bond is breaking, and again this bond is forming. So, alternate bonds are either forming or breaking. So, this is a very well known rearrangement reaction in organic chemistry, and one can use these reactions to convert the ethers to corresponding phenols with a simple reaction just by heating the reagent in a solvent at high temperature. So, we will continue from here in the next class.